I'm Anuradha Mathur. I have been teaching physics at Modern School Vasant Vihar in New Delhi. There are so many materials around us which have special properties because of their state, which is solid, liquid or gas. In the next few minutes, we will try and understand solids and a special property of elasticity. When we look around us and see the solids, they may be looking rigid and strong, while others do not. Even the most rigid rods we know can be deformed if we apply a strong enough force. We have a spring here, and if we compress it, we know it changes shape, but when we release it, it comes back to its original shape. Likewise, if we were to pull it apart, it would become longer, and on leaving it, it will return back to its original shape. I have here some dough, and if I did the same experiment with it, even with a smaller force, this is going to deform permanently. So, property of solids, by virtue of which it comes back to its original shape and size, once the deforming force is removed, is called elasticity. Also, we know that for the same solid, if the deforming force is large enough, it will be deformed permanently. It will not come back to its original shape and size, and this is the property of plasticity. Solids can be classified into two classes, amorphous and crystalline. Amorphous is when the solid molecules and atoms are arranged in a short range order. That means, in the bulk material, they do not have a patterned arrangement. So much so that they do not have a sharp melting point, and they are not rigid. Their properties are isotropic, which means refractive index and thermal conductivity would come out to be the same whichever way you measure it. These, when you break them, are not going to break with regular edges, and therefore, they have special conditioned properties. On the other hand, in a crystalline structure, the atoms and molecules have a long range order. You have a lattice arrangement in which the bond lengths, the bond angles and energies are almost fixed. That means, such materials have a fixed melting point. They also have a rigid structure, and when you break them, they break with sharp cleavages and edges. So, amorphous substances you will recognize as like polythenes, plastics, wax, and on the other hand, the crystalline structure would be with metals or inorganic compounds. To understand this as to what happens to these two types of materials, when we take some deforming force, that means an external force from outside, onto a crystalline structure, it is going to change the bond length, it is going to change the vibration energy of this particular system. So, what will happen when the deforming force is removed? They will come back to their original shape and size. To understand this a little better, let us consider a spring and ball model. In this, the ball is the positioning of the atoms and molecules, and the spring is signifying or showing the positions of bond lengths. The bond energy would be associated with the energy in the spring. So, if you were to displace any of these balls, the spring system will be such that it will try and bring it back to its original position. That means, within the setup against the deforming force, a restoring force is set up, and that is what accounts for elasticity. Robert Hooke, way back in 1635 to 1703, studied the property of springs. He loaded the spring, and the elongation of this he found to be proportional to the load he was applying to it. This later became the Hooke's law, which he presented in 1676. What are the deforming forces? How do they act? What is the effect on materials? That is what we are going to study now. Now, the deforming force will change the shape of the material, a solid structure, depending upon the nature of the material and the way the deforming force is applied and how much of deforming force is applied to it. So, the deformation needs to be measured, and to measure this we use the word strain, which means the change in configuration with respect to the original configuration. So, if you apply a force which is going to change the length of the system, for example, in this case if I apply a force outwards, it is going to be termed as along this line and called tensile or longitudinal force. This will cause a deformity in its length. So, if I were to see it with the dough, this becomes slightly clearer. If I elongate it this way, the tensile strength is responsible for increasing its length. So, how will we measure the strain for it? It will be the change in length divided by the original length. Likewise, what would be the meaning of shear strain? Shear is a word used to talk about the deformation in the shape of the body. This will obviously depend upon how you apply the force. Supposing I get back to my cylindrical condition for this dough, and if I hold it up like this and apply a force tangential to it, the change in shape here is responsible for the shear value, the shear strain. And how do we measure it? From in terms of the deformation caused to one face of the cylinder with respect to the other and the length of this cylinder. So, change in the positioning of the top face with respect to the base and the length between the two faces. Now, there is one more way which we are going to see for the deforming force. That means how we apply the deforming force. For our cylinder, so far we have considered tensile force, which is causing a tensile or longitudinal strain, and we have considered shearing force, which means it is causing a shear strain. The third one that we are going to study is what would happen if we compress this entire cylinder from all sides, so as it shrinks to a smaller cylinder. Obviously, this should strike you that longitudinal strains would be causing a change in the diameter. Volumetric strain, on the other hand, would cause a change in the density of this material. However, not looking at that right now, we are only considering a strain which is going to be measured as change in volume with respect to the original volume. So, we have got now longitudinal strain, the shear strain and the volumetric strain, and for each of them we have a simple way of expressing its magnitude, which is the change in configuration divided by the original configuration. Since the unit on the numerator and denominator is the same, strain has no unit for measurement. Its dimensional formula is m0, L0, T0. Now, we considered the ball and spring model, and we said that once the deforming force is applied, the spring system within the setup, which is obviously due to the bond energy, the bond length, etc., is causing a restoring force to set up inside it. That means, in response to the deforming force from outside, an internal restoring force is set up. Now, the measure of this restoring force is given in terms of stress, and we say it is the restoring force per unit area. Therefore, its unit would be Newton per meter square, and its dimensional formula would be m L minus 1 T minus 2. Now, do you think that only 3 possible ways of applying the deforming forces are there for real bodies? Not at all. You can have multiple ways the deforming force is acting on a body. Consequently, multiple strains happening, and therefore, multiple stresses taking place. But we are not going to look at that in this simplistic picture that we are considering for elasticity right now. So, Is there going to be a relationship between the strain and the stress that is developed inside the body? Yes, there is. And if the deforming force is continuously increased, do you think this value of stress is going to increase continuously? No, because there is an elastic limit. That means a point up to which the stress is going to be proportional to strain, and this is called Hooke's law. So, stress is proportional to strain, or you can say stress is equal to K times strain, and so K is your measure of the ratio between stress and strain and is called modulus of elasticity. You can measure the modulus of elasticity in the lab. You can do so for a wire, and you can also plot a stress and strain curve, meaning thereby you can find the value for strain in terms of original length of the wire that you have taken, place it on a rigid support, hang some load from it, a known value of load per se, and you can find out using a micrometer how much is the extension of this wire. So, extension of the wire, which will be your change in length, divided by the original length, which will give you the value for longitudinal strain in it. Also, the load that you place for it and the area of cross section of the wire will help you calculate the value of stress, which will be force per unit area. And you can divide the two and find the value for Young's modulus, because longitudinal stress and strain are connected by a formula given by Young. Going a little further into this, you can make a graph of stress versus strain. What will this graph look like? This graph is, as you can see, has a typical look. Now, you can ask questions like, will all stress strain curves for all materials look the same? If I use a thicker wire, would my stress strain curve still look this same? Or can we draw similar graphs for volumetric stress and strain, shear stress and strain? What does the graph tell us, and how can we explain such curves? Some of the salient features of the graph are, if you look carefully, there is a region OA. The curve is linear, so Hooke's law is obeyed. Stress is directly proportional to strain. The body will regain its original shape and size. Once the deforming force is removed, the solid behaves like an elastic body. AB section of the graph, stress is not proportional to strain. The body returns to its original shape once the deforming force is removed, because you have yet not deformed it completely. Point B is the yield point or the elastic limit. The corresponding shear is called yield strength, and this is the limit or optimum deformation that this particular system can withstand. Look at the portion BD. The stress developed exceeds the yield strength, and the strain increases rapidly even with small deforming force. What does that mean? That means that the material is going to have more and more strain even with very small deforming force. That means the stress within it is not at all proportional to the strain. At C, the body regains the dimensions, though not exactly, and that is with permanent deformation. This is a deformed condition and we call it plastic deformation. D is ultimate tensile strength. Beyond this point, additional strain occurs with small deforming forces, and point E makes it a point of fracture. That means the material is going to snap apart. It will break into two pieces and therefore will not remain as one unit. So, brittle materials have points D and E which are close to each other, but a large separation between D and E is suggestive of ductile materials. These are the ones that are used for making wires, rods, ropes, etc. So, we have seen that we can place solids in two categories, which will be crystalline and amorphous. Crystalline structures have a regular arrangement of atoms and molecules within them, and that they have regular values of bond length, bond energies. A slight displacement in them by an external deforming force causes this entire setup to be changed. A force of attraction or repulsion results between the atoms, which is the cause for elasticity. We have also seen how we measure this elasticity in terms of deformity created, which is our strain. And we have also checked out that the restoring force which is developed within the body is basically the force per unit area. So, stress is not the same as deforming force, but deforming force per unit area within the elastic limit is the value for stress. You can plot a graph between stress and strain, and that graph has a peculiar shape. You learned the salient features of the graph, and you have also seen that you can find out a modulus of elasticity, which is a measure of the ratio between stress and strain. You also learned the units of all these values. Strain has no unit, stress has a unit of Newton per meter square, and the modulus of elasticity also has a unit of Newton per meter square. In the next episode, we are going to learn more about elastic moduli. We are going to learn ways of finding modulus of elasticity and some applications with the materials around us on the basis of elasticity. Engineers and product designers make use of this knowledge about elasticity of the material and choose it for different purposes, making bridges, making trolleys, making shoe soles, making tires. All of this means you must know the elastic property of that material in that condition, and that will be the way for making new things, new innovations for useful purposes.